Well, welcome back. We're in section 4.1 now, chapter 4, and we're looking at polynomial arithmetic and division algorithm. So we're going to be looking at polynomial rings. And as we look at these new different kinds of rings, remember you're catching patterns. And a lot of this pattern is coming from what we did with the integers in chapter 1 and chapter 2. So keep that in mind because you're going to see that system throughout the material that we covered. So, polynomial rings. Remind yourself, a polynomial is a function that can be written in the form of f of x equals a sub n x to the n plus a n minus 1 times x to the n minus 1 plus dot 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 plus a1x plus a0, where the n is a positive integer, so all the exponents of the x's are going to be positive integers, and the ai are the coefficients, all the coefficients in terms of all the x terms, and this is the constant coefficient. So the a sub i's are the coefficients. So in the notation of r adjoined x, and that's how you would read this, r adjoined x, r is the ring where the ai's are elements of r. So the coefficient in front of my x's are going to be elements of r. And the x is the variable, also known as the indeterminate. X is not a part of r, it's just an indeterminate, it's x. So, f of x will be an element of r adjoined x if the ai's, which are my constant terms, my coefficients, are elements of r. So we're looking at polynomial rings, and you've played with polynomials ever since junior high school, but we're going to look at this where the coefficients of each of the x terms are going to come from a special ring R, whether that ring be the real numbers like you do in high school, or maybe the rationals, or better yet, maybe z mod 6 or z mod 7, or 2 by 2 matrices that we're going to be able to put in front of these variables and stuff. So there's lots of options that we have for the ring that we're going to attach to the indeterminate x. Theorem 4.1 says this: if R is a ring, then there exists a ring T containing an element x that is not in R that has the following properties. So Theorem 4.1 is trying to make this polynomial ring very general. So if you have a ring R is a ring, and there's going to exist another ring T that contains an element x. So x is contained inside of T, but that is not in R, that has the following properties. R is a subring of T. X times a equals a times x for every a in R. So this base ring will be contained inside of, be a subring of big T. X commutes with every element in R. That's what property number 2 says. Number 3 says the set R of x of all elements in T of the form of, it's the polynomial, a0 plus a1x plus a2x squared plus dot 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 plus an x to the n, where n is greater than or equal to 0. It's going to be positive integers here, and the ai's are elements of R, is a subring of T that contains R. So R is going to be a subring of T. So let me explain this part. T are actually polynomials. But if the coefficient in front of x, x squared, x cubed, all the way up to x to the n are all going to be 0, that leaves you with a constant term. And the constant term can come from R. So the constant term is going to be contained inside of this T, but the constants come from R. That means that R, actually that ring that the coefficients come from, will be contained inside of T, and R will be a subring of T. The representation of the elements of R adjoined x are unique. This is the unique element that's going to be in this R adjoined x. And number 5, if you got this polynomial, a sub 0 plus a1x plus dot 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 plus an x to the n, if you set that equal to 0, that will be the case if and only if each of the coefficients are equal to 0 for each one of these AIs. So the coefficients have to be 0 for the polynomial to be equal to 0. So we're talking about polynomials here. So we're looking at this R adjoined X, and it depends on what kind of ring R you happen to join this guy and what kind of properties your polynomial rings are going to have. So if we come over here to Theorem 4.2, Theorem 4.2 tells me this. If R is an integral domain, I'll remind ourselves what an integral domain is. An integral domain is a commutative ring with identity with no zero divisors. And f of x and g of x are non-zero polynomials in R joined x. Okay, remember R is an integral domain. Then we're going to have this situation that the degree of f of x times g of x will actually be equal to the degree of f of x plus degree of g of x. Now this is something that we talk about and study in high school about degrees of polynomials. Definition degree is the largest exponent in your polynomial. And so when you have two functions, two polynomials being multiplied times each other, you typically FOIL or distribute them out. And when you multiply, you add exponents. That becomes the reason for the degree of f of x times g of x is equal to the degree of f of x plus degree of g of x. But you gotta have an integral domain. Why an integral domain? Because integral domains do not have zero divisors. You don't have non-zero elements multiplied by other non-zero elements that actually give you 0. So because of that, this property from high school about degrees will continue to hold. Corollary 4.3 of this theorem 4.2 says this. If R is an integral domain, then so is R adjoined X. If R, where the coefficients come from, is the integral domain, then R adjoined X is also going to be an integral domain. You won't have any zero divisors in your polynomials. There's no way to get a non-zero polynomial times another non-zero polynomial to actually give you 0. And because the coefficients commute, the integral domainness of R will transfer into the polynomial ring being also an integral domain. Corollary 4.4 says this though, that R be a ring. R is going to be a general ring. Pick your favorite. Basic ring, commutative ring, ring with identity, whatever kind of ring you want. If f of x and g of x and f of x times g of x are non-zero in R adjoined x, then the degree of f of x times g of x will be less than or equal to the degree of f of x plus degree of g of x. Notice the new thing they put in there, that less than or equal to. We know if R is an integral domain, this is an equal to. The problem is, what if R is not an integral domain? Then you're going to get this inequality. The degree of f of x times g of x will actually be less than or equal to the degree of f of x plus degree of g of x. So let me give you an example of that. And the way I put my little notes here, I needed another sheet of paper. So here's my sheet of paper here for my example. So here's my example right here for you guys. In Z6 adjoined x, let f of x be equal to 3x squared plus 2x plus 1 and g of x be equal to 2x squared plus 5. Now notice how I wrote this. What is the ring where the coefficients come from? Z6. They're the equivalence classes from 0 through 5. So I got to have as coefficients in front of my x terms and my constant term have to be members of Z6. 3, 2, 1, 2, and 5. So all these are equivalence classes of Z6. Now, let's just check it out here. What is the degree of f of x? Well, what's the largest exponent? It's 2. And what is the degree of g of x? Well, this is 2x squared plus 5, so the largest exponent, again, is 2. So the degree of f of x is 2, and the degree of g of x is 2. However, let's take a look at this guy. what would f of x times g of x be equal to? Well, f of x was equivalence class 3 x squared plus 2 equivalence class 2 times x plus equivalence class 1 times equivalence class 2 times x squared plus equivalence class 5. Now again, if I'm going to multiply polynomials, I go back to junior high school and I'm going to FOIL this thing out. I'm going to distribute. So let's do that. So this would be equal to, here we go, what is 3x squared times 2x squared? That's officially 6x squared plus 3x squared times equivalence class 5 would be 15x squared. I know the coefficients need to come from, by the way, this is x to the fourth here, but the coefficients have to come from z6. I'll convert them later. So 3x squared times 2x squared is actually 6x to the fourth, excuse me there. X squared times an x squared is x to the fourth. 3x squared times 5 is going to be 15x squared plus 2x times 2x squared would be 4x cubed. 2x times 5 would be plus 10x. 1 times 2x squared is plus 2x squared. And then last, 1 times 5 is plus 5. As I squeak this guy in. Now, typically with polynomials, we like to write these guys in decreasing order. So this would be equal to equivalence class 6 x to the fourth. The next one would be the cubes plus equivalence class 4x cubed. So 6x to the fourth plus 4x cubed. I put little lines to them when I've used them. Let's see, the next one would be x squared. And I got two of those. I got 15x squared plus 2x squared would make it plus 17x squared. And then I got plus 10x plus 5. So this is what f of x times g of x is. But remind ourselves, these are polynomials in z6 adjoint x. So to be an element of z6 adjoint x, I have to have f of x times g of x. I have to go convert these coefficients. What is 6 equivalent to in z6? 6 is 0, x to the fourth. 4 is a good equivalence class in z6. That would be plus 4x cubed. 17. Well, how many times does 6 go into 17, and what would the remainder be? Well, it goes in there 2 with a remainder of 5. So 17x squared was the same thing as 5x squared, equivalence class 5x squared, plus equivalence class 10 in z6 converts back to equivalence class 4x, and equivalence class 5 is good. That is actually in z6. So, and this is gone because 0 times anybody is 0. So that gives me f of x times g of x is equal to equivalence class 4 times x cubed plus 5 times x squared plus 4 times x plus 5. And then I ask you the question, what is the degree of f of x times g of x? Well, because of those darn zero divisors, because z6 is just a commuted ring with identity, when I multiply my two leading coefficient terms, they end up knocking each other out and giving me 0, which now makes the degree of f of x times g of x equal to 3. And you'll notice that the degree of f of x times g of x, which is 3, is actually less than, equal to, but it's less than the degree of f of x plus the degree of g of x, because the degree of f of x was 2 plus the degree of g of x is 2, and that's 4. 3 is less than 4. You'll never get greater than on the product, but it'll be less than or equal to. And when the polynomial that's attached to the x's, where the polynomial the ring attached to the x's for these polynomial rings, when the ring is an integral domain, then you're going to get the fact that this will actually be equal to each other, because you won't have to worry about terms killing themselves off. But when you just have arbitrary rings, you're going to get that formula: the degree of f of x times g of x is less than or equal to the degree of f of x plus the degree of g of x. So as we go back here and look at corollary 4.5, and corollary 4.5 says this: let R be an integral domain and f of x be an element of R adjoined x, then f of x is a unit in R adjoined x if and only if f of x is a constant polynomial that is a unit in R. In particular, if f is a field, the units in f adjoined x are going to be the non-zero constants in f. All right, remind ourselves what a unit is. A unit is a multiplicatively invertible element. That you got an element that there exists another element inside the ring, since the product is actually equal to 1. It's an invertible element. Now, so if you've got a polynomial, now polynomial being a unit, now let's talk about a unit. That means it has to be invertible. So again, we're talking about polynomials here. So if I take my standard polynomial, and here was my example sheet over here, so I kind of taught you guys about it down here. So if you got your standard polynomial, let's make that sucker kind of small. How about 2x plus 5? G of x is equal to 2x plus 5. What is g of x inverse going to be? What is the inverse of that element, multiplicatively speaking? Well, now in terms of the polynomials, you want to get the identity, which is 1. The one polynomial of x equals 1. That would be your identity, because 1 times anybody is anybody. So the inverse would be 1 over 2x plus 5. That is the inverse of 2x plus 5, is 1 over 2x plus 5. Now that's awesome, but here's the problem. This is a polynomial, degree 1. This is a rational function. It's not a polynomial. So not polynomial. So 1 over a polynomial typically is not going to be a polynomial unless your polynomial is a constant. If g of x is 5, then g inverse of x would be 1 over 5. And so that would actually be okay. You can have a constant polynomial. And that's what this corollary is actually telling you. So again, the corollary states this: that let R be an integral domain, so you don't have to worry about your zero divisors, and f of x is an element of R adjoined x, then f of x is a unit in R adjoined x if and only if f of x is a constant polynomial that is a unit in R. So the only units in a polynomial ring are going to be the constant polynomials, f of x equals 27 or whatever it is, where that element that you're equal to is a unit in the actual ring that you're adjoining x to. And in particular, if we have a field, remember your definition of a field, which is an integral domain with all non-zero elements or units, then all non-zero elements that are in f, you make them polynomials. F of x equals 5, those constant polynomials, those guys will actually be the units in f adjoined x. So as we get into this stuff, look for patterns. That's going to be the key. So, Theorem 4.6 says this: the division algorithm in f adjoined x. Let f be a field, and f of x and g of x be elements of f adjoined x. And this time I'm attaching a field to this guy, not just any arbitrary ring. I want a field, because I like that idea that all non-zero elements are invertible in a field. But now we're attaching it to x, so we're looking at the polynomial ring here. So let f be a field, and f of x and g of x be elements of f adjoined x, with g of x not equal to the zero polynomial, zero constant in f. Then there exists a unique polynomials, q of x and r of x in f adjoined x, such that f of x is equal to g of x times q of x plus r of x, and either r of x is equal to 0 in f, or the degree of r of x will be less than the degree of g of x. we're talking about dividing polynomials. And when you divide polynomials, it works the same way as when you divide integers. So your dividend is equal to the divisor times, we use Q for a reason, the quotient polynomial plus the remainder polynomial. But when we talk about the remainder polynomial, then we talk about it having to be less than, but to be less than in terms of polynomials, you look at the degree. So the degree of your remainder has to be less than the degree of the divisor. That's what's going on here. Or the polynomial is actually equal to 0. So we're going to be dividing polynomials. So I got another example for you here. Using the division algorithm in f of joint x, what is 4x to the 5th minus 2x squared plus x minus 2 divided by x squared plus 2x minus 1? But I got to tell you, remember, you're in modern/abstract algebra here. Anytime somebody gives you a polynomial from this day forward, you got to ask yourself, well, where did the coefficients of my variables come from? You got to know what ring you're going to be in. We're in Q adjoint x. And remind you, Q was the rational numbers here. So integer divided by an integer is where these guys come from. And remember, the rationals are a field. So this is a field adjoint x. So I want to use and write this up in the division algorithm. Well, first thing I want to do is I want to divide it. So I'm going to go old school here, long division. My dividend is 4x to the 5th minus 2x squared plus x minus 2. Notice that all the coefficients in front of the x terms are rational numbers. They're actually integers, but the integers are also rational numbers here. But remember, if there is a term missing, you got to put a 0 in for it. So you end up getting 4x to the 5th plus 0x to the 4th plus 0x cubed, because there is no fourth degree term, there's no third degree term, minus 2x squared plus x minus 2 divided by, this is your divisor, x squared plus 2x minus 1. So just put these zeros in there. The terms were missing because that's where most people would screw this up. If there's a term missing, whether it be in the dividend or the divisor, always put a 0 in for it because you want these polynomials to be in decreasing order. Now let's play the game. We're talking about in rationals, so we can play with fractions, but I gave you some nice numbers here. What times x squared is going to be 4x to the 5th? That's going to be 4x cubed. And once you've identified, you multiply through, you distribute. 4x cubed times x squared is 4x to the 5th. 4x squared times 2x would be plus 8x to the 4th. 4x cubed times a minus 1 is a minus 4x cubed. Now I'm going to subtract, which changes my signs. Remember about your long division days here. And the first term should always cancel. If it doesn't, you screwed it up. 0x to the 4th minus 8x to the 4th is a negative 8x to the 4th. 0x cubed plus 4x cubed is plus 4x cubed. You bring down your next victim, minus 2x squared, and you play the game all over again. What times x squared is negative 8x to the 4th? That is going to be negative 8x squared. I distribute. Negative 8x squared times x squared is going to be a negative 8x to the 4th. Negative 8x squared times 2x will be minus 16x cubed. Negative 8x squared times a negative 1 would be a positive 8x squared. Notice all your like terms line up when you put those zeros in there. I'm going to subtract, which is going to change my signs. This becomes a plus, this becomes a plus, and this one becomes a minus when you change your signs. And the first term should cancel. Negative 8x to the 4th plus 8x to the 4th cancels. 4x cubed plus 16x cubed is 20x cubed. Minus 2x squared minus 8x squared is minus 10x squared. I bring down my next victim, plus x. What times x squared is 20x cubed? And that's going to be 20x. So it'll be plus 20x. 20x times x squared is 20x cubed. 20x times plus 2 is plus 2x. That would be plus 40x squared. 20x times minus 1 is a minus 20x. Then I'm going to subtract, which will change my signs. Remember your long division days from junior high school. So this will cancel. Minus 10x squared minus 40x squared is actually minus 50x squared. X plus 20x becomes plus 21x. Bring down your last victim, minus 2, and then play the game all over again. What times x squared is negative 50x squared? That would be minus 50. When I multiply, I get minus 50x squared. Minus 50 times positive 2x would be minus 100x. Minus 50 times a minus 1 is a plus 50. And now once again I subtract, which will change my sign. So plus, this one becomes a plus, this one becomes a minus. The first term should always cancel. 21x plus 100x is 121x. Minus 2 minus 50 is minus 52. Since x squared doesn't go into an x term, this is my remainder polynomial. This is my quotient polynomial. Remainder polynomial, quotient polynomial. Therefore, by, remember 3 dots in triangular fashion means therefore, by the division algorithm, the dividend, which is 4x to the 5th minus 2x squared plus x minus 2 is equal to the divisor, which was x squared plus 2x minus 1. This, by the way, is the divisor. I call him little d of x there. The divisor, this is my quotient, q of x up here. So it's the dividend is equal to the divisor times the quotient plus the remainder. So the divisor was x squared plus 2x minus 1. The quotient is up here, is 4x cubed minus 8x squared plus 20x minus 50 plus the remainder of 121x minus 52. Now I have my polynomial 4x to the 5th minus 2x squared plus x minus 2 equal to 2x squared plus x squared plus 2x minus 1 times 4x cubed minus 8x squared plus 20x minus 50 plus 121x minus 52. So that gives me the divisor times quotient plus remainder. I've rewritten my polynomial in the form of the division algorithm. This is working very similarly to what we did in chapter 1 with the division algorithm with integers. We're just playing around with polynomials now, but we're doing the same thing. So catch that pattern all the way throughout chapter 4. It'll be important.